Okay, I want to begin by comparing three different scenarios. You guys should be familiar with everything that's on the screen right now. Here I have a ball rolling down a hill. You guys are aware that as it rolls down, it's going to start accelerating. Its velocity will be increasing. I'm calling the right direction positive. It starts out at the origin, we'll say, just to make it simple. So here you can see the position is increasing faster and faster, speeding up. The slope of this line is increasing. It's getting steeper and steeper and steeper. So the velocity is changing. The velocity is becoming more and more positive. It's moving faster and faster to the right, which means it has some constant acceleration. It's moving down the hill. This is the most boring example, but it is important for us to look at. This is a ball that's just sitting on a table. The velocity is zero. It's not moving to the left or the right, it's just sitting still. So its position is not moving at all. It has no displacement as time goes on. The x value does not change. It is staying at that position. Because it's not changing position, the velocity is zero. Because the velocity is not changing, the acceleration is zero as well. This ball here, this is going to take some imagination. This ball is moving on a surface. But let's say that this surface has no friction, that when the ball rolls and comes into contact with the tabletop, that it is frictionless. This is actually impossible, but it's a very important thought experiment for us to think about. There's no friction. So the ball is just rolling. Because there's no friction, there's nothing pushing or pulling it, the velocity is not going to change. This ball is not going to slow down. Theoretically speaking, as we'll see later, this ball should keep rolling forever until it falls off the edge of the table, I guess, because there's nothing to slow it down. There's no friction to oppose its motion. So it has a constant velocity, positive velocity to the right. So here you can see my position time graph. The position is increasing as time goes on. One constant velocity. And because the velocity is constant, yet again, we have no acceleration. So three very important cases that really covers all the possibilities in terms of motion. We can have an object that has acceleration. We can have an object that is not moving at all. And we can have an object that is moving but has no acceleration because the velocity is constant. So look at these and try to figure out which one stands out. Which one seems to be the most interesting, the most different? Hopefully you guys are realizing that the most interesting scenario here is this one. Because what is it doing? It is changing its velocity. Its velocity is increasing. It's speeding up as it goes down the hill. It has an acceleration. These other two objects do not have acceleration. Their acceleration is zero. Their velocity is constant. Even the ball that is moving at a constant velocity, yeah, it's moving, but it's not speeding up or slowing down. Its motion is not changing. Both of these are actually similar because we could say that their motion does not change at all. No change in motion, no delta V, no acceleration. Whereas this one does have acceleration. That's very interesting. And this leads us to a very important question. What causes a change in motion? That is the question that we have to begin exploring. What causes a change in motion? Notice I'm not asking the question, what causes motion in the first place? I'm asking the question, what could cause motion to change? What's causing this ball to speed up? What's causing its velocity to increase? What is changing its motion? And we want to explore now this question, what causes acceleration? What causes a change in motion, a change in velocity? And in order to do that, we have got to begin exploring the concept of forces. Okay, in order to understand everything I'm about to tell you about forces and how forces and objects interact to cause changes in motion, you really need a brief history lesson about how all of this was developed. Um, we need to start our history lesson with this guy over here on the left. His name is Aristotle, and he was an ancient Greek philosopher, the student of Plato, who lived in about the 3 or 400s BCE. Aristotle developed many different scientific theories. He wrote a book called The Physics, which is really one of the first attempts to formally set down a theory about the natural world, how things move, things like that. And his theory went kind of like this. He said that every object has some sort of inner potential, and that motion was that inner potential being actualized. He thought that when you pushed a rock to start it rolling down a hill, or when you threw a ball or something like that, anything that caused motion to be set in action, to set an object in motion, that you were kind of delivering, giving that object some sort of vital motive, motion, force, or energy. It flowed out of you and it flowed into that object so that that object's potential could become actual. So you were, in effect, transferring a piece of you into that object, causing it to actualize its motion. It was this idea of almost a fluid that passed between objects, from one object to another. He also thought that motion and changes were controlled by what he referred to as teleological forces. This word teleology, it deals with what we call ends or goals. So he thought that objects kind of had internal natural goals that they were sort of programmed to fulfill. An example to help you understand that. Imagine you pick up a stone or something heavy. It could be a heavy ball, or even if you're cutting down a tree, the tree is heavy. In each of those cases, you know what's going to happen. The object is going to fall straight down to the earth. In order to understand and explain that, Aristotle said that, well, it's the teleology, it's the natural end or goal of heavy things to fall toward other heavy things. If the earth is the heaviest thing there is, then of course stones and balls and trees that you're chopping down, all of these heavy things, are also going to fall to the earth. It's their natural goal. It's kind of where they fit in nature. Everything wants to move toward where it fits in nature, to its end, final resting place, to the perfect goal, so to speak. He thought humans worked in the same way, that we have some sort of teleological end that we can pursue. He called it the good or virtue, things like this. Another example is take the rock again. A stone or a rock in your hand is made of the same stuff that the earth is made of. So if you drop it, because the earth and the stone are made of the same matter, the same type of matter, he thought there were four elements: earth, fire, air, and water. That the earth element, the stone rocky bits that make up the stone and the earth itself, that they belong together, that their natural end or goal was pre-programmed to fit together, to lock together. That's why stones or heavy things fall. Heavy things have more of an earthy element in them. They have more of the element earth, and all the element of earth belongs together. So things with that element, heavy things, stones, are going to fall down and find their natural resting place, their final end, their pre-programmed goal on the earth. We know that's kind of silly now, but that's what people held for a long time, even through the Middle Ages, when Aristotle's writings were kind of rediscovered, and people really started studying and considering these things again. And he also said that in order for something to move at all, it must have a force behind it. So Aristotle would look at our example earlier, where we had that ball rolling along a smooth, frictionless surface, and Aristotle would say, aha, that ball is moving, so there has to be a force applied to it at all times to keep it moving. That there must be some push to keep it going. Forces have to cause all motion. That makes some common sense. But, as we're going to see, that is not the case. Just because an object has velocity, just because an object has motion, does not mean that there's some mysterious force pushing it or pulling it. So Aristotle's ideas were held all the way up until the 15 and 1600s, when these guys came along, Galileo Galilei and Isaac Newton, and they started scientifically studying moving objects. Galileo has a famous experiment where he supposedly, it's kind of a myth, but he dropped objects off the Leaning Tower of Pisa to show that they would fall at the same rate. We'll talk about that. That has to do with gravity. And Newton is the one who's really famous for studying forces and motion in the first place. And finally, once and for all, setting down really the foundation of classical physics of this class, talking about velocity, acceleration. And remember, we're asking the question in this portion of the unit, our guiding leading question, the important question we're trying to answer is, what causes acceleration? What causes a change in motion? Why would an object speed up or slow down? What causes that? Newton is the first one to really answer that question. What's really interesting about Newton is that in order to study these things, he needed to invent a brand new realm of mathematics. It's called calculus. Yeah, Newton is one of the guys who invented calculus. Imagine being so smart that you invent calculus. He didn't invent it at the same time as a guy named Leibniz in Germany. Newton was English. We actually use Leibniz's notation and his symbology in calculus today. So maybe Leibniz should get more of the credit. But anyway, Newton used and invented calculus in order to study these things, study motion. So Galileo and Newton, they laid the groundwork for all physics. This entire class actually could not exist without them. Thank you, Galileo and Newton. But together they said these general things, contrary to what Aristotle said thousands of years before. They said that all objects have the tendency to keep the motion that they already possess, that objects don't want to change their motion. This makes some pretty good common sense. Imagine a giant boulder that you're trying to roll for some reason. Maybe you're Sisyphus trying to roll it up a hill. Does that giant boulder want to roll up the hill? No, it wants to keep the motion it has, which is no motion. Imagine that you do roll the boulder up a hill and it starts rolling back down the hill. Is it going to want to stop rolling? No, not very easily. It's going to roll and roll and roll and roll and roll unless something opposes it. So objects have the tendency to keep the motion they already possess. We're going to talk about that more in a bit. Instead of being controlled by those teleological forces, those natural pre-programmed goals or ends, if something possesses more of the earthy element, then it's going to fall to the earth. Things like this, very odd, kind of strange, almost supernatural ideas. They said, no, we can determine and calculate how forces control motion. These forces are not teleological, pre-programmed, end, perfect goal type forces that an object is drawn to, but rather the forces cause and control motion. We can determine what they are. We can make calculations. We can make predictions. We can set them down with mathematics, with scientific rigor, instead of saying, oh, the rock fell to the earth because they both possess more of the earth element, and everything that has more of the earth element wants to belong together because that's right, that's good, that's their natural final end and pre-programmed goal. No, come on, we need to be more specific, more scientific, more mathematical about it. And then finally, this is the most important part that I want you guys to get. Forces do not cause motion. If an object is moving, it does not necessarily mean that there is an overall force pushing or pulling on that object. Instead, it's the interaction of forces that cause objects to change their motion. Remember, we're asking the question, what causes objects to change their motion? Why would an object accelerate? Why would it speed up or slow down? Especially because we've just discussed briefly, and we'll discuss more later, that objects tend to not change their motion. They tend to keep the motion they already possess. So what causes that? Just because an object is moving, once again, if a ball is rolling on a table without any friction, just because that's moving doesn't mean there's a force acting on it. But when it changes its motion, when it speeds up or slows down, that is from the interaction of forces, and that's what we're going to talk about.